10.0.2.10. Then the second one is 10.0.2.11. You can again notice the rule here. The network part is the same for all devices and for the gateway. In our third network, we got the same situation. The gateway is 10.0.3.1, and the end devices have addresses that begin with 10.0.3. Now that we've covered the types of addresses we would assign to gateways and end devices, we need to talk about two other IP addresses that are very important. The network address and the broadcast address. The network address is the very first IP address in a subnet. In the previous slide, we gave the first useful IP address, or the first usable, I believe is the term, IP address to our gateway, but that's not really the first IP address. The very first IP address in this subnet would be 10.0.3.0. Here we have an example, 81.2.0.0, where the first two octets are the network portion and the second two octets are the host portion. The network address has its host portion filled with zeros, and the broadcast address is the opposite. A broadcast address is the very last IP address in a subnet. Here's an example, 81.2.255.255. So 81.2 is the network portion, and 255.255 is our host portion. Hopefully you can notice our host portion this time is filled with ones, and this is what it looks like in binary format. We have 8 ones in the third octet and 8 ones in our fourth octet. Now let's look at some examples. The right part of this network is actually the same network from our previous example, but now we've added one router, which gives us 2 additional networks. We have this network between the 2 routers and this small LAN with 2 laptops. We're going to describe these 2 networks with their network addresses or their network IDs. This point-to-point network, a point-to-point network is a simple network between 2 routers. It's going to be 9000. So this is our network ID. The small LAN with 2 laptops is going to be 8000, and here are the end host IP addresses in these 2 networks. So we assigned the router on the left with 9001 and the router on the right with 9002. These are the 2 IP addresses we're going to use in this network, and in this network we're only going to need 3 IP addresses, one for the gateway and one for each of the laptops. They're going to be 8001 and 80010 and then 80011. Now let's think about what are the network IDs for the 3 networks we had in the previous example. I'm just going to make this easy and display the network IDs. For the first network, it's going to be 10.0.3.0, as we've talked about in the previous slides. So the network ID is the network portion of an IP address, and then the host portion filled with zeros. The other 2 networks are obviously going to be 10.0.1.0 and 10.0.2.0. The next thing we're going to talk about is what are these network IDs or network IP addresses actually used for. And the example I'm going to give you is going to be related to routing. So we're going to look at how do we build routing tables and what do they actually look like. So we're going to circle this 10.0.something network, and we're going to name our routers R1 and R2. We're also going to have to name the interfaces on our routers. So they're going to be interface 1 and interface 2 on router 1, interface 3, 4, 5, and 6 on router 2. And then we're going to look at what the routing table in router 1 looks like. A routing table lists the different networks that this router can reach. So router 1 can get to all these networks by simply sending packets to different interfaces. So a job of a router is actually to just get rid of a packet as soon as possible. Now, for example, if router 1 didn't have an entry for the network 10.0.3.0 in its routing table, it wouldn't be able to reach that network. So if it received a packet with a destination IP address that belongs to that network, it would just drop the packet because it doesn't really know where to send that packet. Fortunately, we do have an entry for that network, so router 1 is perfectly capable to send packets to that network. But now let's do something a bit advanced, and we'll cover this topic further in our future lessons. But I just want to show you what's possible with IP addressing and or IP subnetting in this example. We're going to look at this 10.0.123 network, and I promise to explain what this means further in probably the next lesson. But for now, just know that /16 means that the first 16 bits represent the network portion of this IP address of 10.0.0.0. So what I want to do here is I want to replace these 3 entries in our routing table with only this. Why can I do that? So when router 1 receives a packet with a destination address of 10.0.2.50, for example, okay, even if it doesn't exist here, let's say we add a new device here and we give it that address 10.0.2.50. So say that this laptop wants to send a packet to that imaginary device. Okay, so this router will look up the destination IP address, which is 10.0.2.50 in its routing table, and it's going to say, okay, so I have a route for 10.0.2. Something, so anything. So this is a network address. It represents all hosts within 10.0.2 network. But before router 1 can reach this route, it has to go through all the other routes. So what I want to do is I want to simplify the process here. I'm just going to replace these 3 routes with one route. So this is basically called a summary IP address, but we'll talk about that later, I promise. But for now, what happens here is this router receives a packet with destination address 10.0.something. So the last 2 octets could be anything. So it doesn't have to go through 3 routes. Instead, it only goes through 1 route because anyway, it's going to send a packet with a destination address of 10.0.anything through interface 2. I hope that made sense. We'll talk about this further, but just to give you an idea of what's possible to do with IP addressing. And now we're going to talk about broadcast addresses, what they are, and to give an example of how they work. We've already defined our network IDs for all of our networks in our example, and I'm going to use the CIDR notation once again, and I promise that the next lesson is going to be about that, and we're going to do more examples. But for now, just know that /24 means that the first 24 bits, or 3 times 8, which is 24, or the first 3 octets represent the network portion. So 8.0.0 is our network portion, which is exactly 24 bits. So how do we figure out what's the broadcast address there? Well, we simply take the host portion and we turn it into ones in binary format. In decimal format, when we have 8 consecutive ones, that's 255. So the broadcast address here is going to be 8.0.0.255. So 8.0.0 is our network portion, and this last octet is our host portion. If it's filled with ones, it's going to be the broadcast address, and if it's filled with zeros, it's going to be the network ID or the network IP address. Now let's look at the other networks. So for 9.0.0.0/24, that's going to be, the broadcast IP address is going to be 9.0.0.255. Hopefully you can already guess what the broadcast addresses for the other 3 networks are. So we're going to use the /24 for all 3 of them, and all 3 of them are going to be the same network portion, and only the host portion is going to change from 0 to 255. Let's look at an example. Let's say that this laptop sends a broadcast packet with source address, its own address 10.0.3.12, and destination IP address is going to be our broadcast address for this subnet, which is 10.0.3.255. So once this laptop sends its broadcast packet, it's going to end up on the switch. The switch is going to send this packet through all of its interfaces except for the interface that received the broadcast packet. So these are the devices that end up receiving the broadcast packet. Now, if you're wondering what is the router going to do, is the router going to further forward this broadcast? It's not. So routers do not forward broadcast packets. Hopefully that's clear enough. We're just going to look at one more example of how to determine a network ID address and how to determine a broadcast address. So in this example, we're going to use host address 153.0.99.207. And this is the binary representation of this address. The red part is going to be our network portion, and the blue part is going to be our host portion. So to determine our network address, we're going to just copy the network portion, and into the host portion, we're going to put all zeros. So this is our network address. It's actually going to be 153.0.0.0. How do we determine the broadcast address? We're going to copy the network portion, and we're going to use ones instead of zeros in our host portion. There you go, guys. That's it for this lesson. We'll talk about network masks and the CIDR format and all of this further in our future lessons. See you there. All right, so I know I promised the next thing we would talk about would be CIDR, but before there was CIDR, we had classful IP addresses, and we really need to talk about those before we go any further. So I suggest we get right to it. At the very beginning, when we just started allocating IP addresses to computers, things were a bit different. Everyone thought that we would always be able to separate three sizes of networks: large networks, medium networks, and small networks. And the idea behind classes was that once a company or a university would want to get an address range, they would be given a range depending on the size of their network. So Class A networks were only supposed to be given to very large networks. And that is because in a Class A network, the first 8 bits or the first octet is the only octet that represents the network portion of that address. That means that there is only 256 Class A networks. One Class A network has 2 to the power of 24 different host addresses or different combinations for the host portion of the address. 2 to the power of 24 is somewhere around 16 million addresses. Now, hopefully you'll agree with me that there's probably not many networks in the world that actually need that many public addresses. The next class is Class B, which is somewhere between Class A and Class C. Class B networks have 2 octets representing the network portion of the address. The other 2 octets represent the host portion of the address. These were meant to be given to medium networks, and then Class C networks were meant to be allocated to very small networks. A Class C network is kind of opposite from the Class A network because Class C networks have its first 3 octets representing the network portion and only 1 octet representing the host portion. So one Class C network can only have 256 different IP addresses in one subnet. Now, one more thing, there are actually additional 2 subnets, classes D and E. D is reserved for multicasting and E is experimental and is used for research and documentation. Now let's look at some examples. Here's a Class A network 71.3.99.2. This is the network portion. So 71, the first octet, is the only octet that represents the network portion. The other 3 octets represent the host portion. Now, how do we determine the network address? So we take the network portion, we copy that, and then in the host portion, we put zeros. So 71,000 is going to be our network address for this example. Now, how do we determine the broadcast address? It's similar. So we also need to copy the network portion, which is 71, and then in the host portion, we're going to put all ones. Of course, this is in binary format. So when you convert 8 ones to a decimal format, you're going to get 255. So we're going to have 71.255.255.255. Now, how do we actually know to which class does a certain IP address or an IP range belong to? We determine that by looking at the first octet. So Class A addresses are somewhere in between 1.0.0.0 and 126.255.255.255. So if we have the first octet ranging from 1 to 126, we have ourselves a Class A IP address. Let's look at another example, this time from class B. 155.8.101.33. So in a class B network, the first two octets represent the network portion, and then the last two octets represent the host portion. So what is the network address in this example? Again, we're going to copy the network portion, which is 155.8. And then in the host portion, we're going to use all zeros. Of course, all zeros in binary format are the same in decimal format. So the network address is going to be 155.8.0.0. Now the broadcast address is going to be 155.8. That's the network portion. And in the host portion, we're going to use all ones. And just as in the previous example, 8 ones in binary format equals to 255 in decimal format. And how do we know that an IP address belongs to class B? So again, we look at only the first octet. And if the first octet is somewhere between 128 and 191, that is class B address. Let's see our third example, this time from class C. So here we have 201.65.4.137. Here, the first three octets represent the network portion, and only the last octet represents the host portion. As in the previous examples, we're going to determine the network address, and we'll get the network address by copying the network portion, 201.65.4, and then in the host portion, we're going to put 0. So that is our network address for this example. Let's determine the broadcast address. To determine the broadcast address, we're going to copy the network portion, and in the host portion, we're going to put all ones. Again, we're going to have 255 for each segment or each octet that represents the host portion, and since we only have one, it's going to be 255 at the end, and that's our broadcast address. Now, how do we know that an address belongs to class C? So once more, we look at the first octet, and if it's somewhere between 192 and 223, that's a class C address. Everything above 224 or everything above all IP addresses that start with 254 and upwards are going to belong to those two additional classes, class D and class E. Finally, as I promised some slides ago, here's the table that summarizes all 5 classes. As we've already learned in the examples, we recognize all 5 classes only by looking at the first octet. So here's the first octet, here's the second octet, here's the third octet, and here's the fourth octet. Class A addresses, or rather the first octet of class A addresses, ranges from 1 to 126. Then we skip 127, which is reserved for loopback, and class B starts at 128 and ends at 191. Class C begins at 192 and ends at 223. And let me clarify one more thing. So regardless of what the first octet is, each of these classes can have absolutely anything in the other octet. So it's only important to know what we have in the first octet. That is how we determine the class. All the other octets are just combinations of network portion and host portion of the IP address. All right, now that we're done with the table, let's go through some additional examples. So 200.200.200.200. Question for you is, which class does this IP address belong to? as we discussed, we only look at the first octet. So the first octet is 200. That, looking at this table again, would be class C. All right, let's go to the next example. 1.1.1.1. This is definitely class A. Next example is 192.168.1.1. This is probably the most familiar IP address, and it belongs in class C. Fourth example, 44.13.0.0. So this is also class A because the first octet is between 1 and 126. Fifth example, 100.0.0.255. This is also class A. And the last example would be 155.255.255.7. So the first octet is 155. Class A is between 1 and 126. Class B is between 128 and 191. So this IP belongs to class B. And that would be all for this lesson. See you in the next one, where we definitely talk about CIDR. As promised, in this lesson, we're going to talk about CIDR. CIDR stands for Classless Interdomain Routing, and we're going to start with an example right away. So we're going to use a class B address from the previous lesson, and what we're going to do is we're just going to change its mask. First, let's go through this example. So this is a class B address, 155.8.101.33/16. So /16 means that the first 16 bits of this IP address represent the network portion. So if we have 16 bits, that's 2 times 8, that's exactly 2 octets. Now to get the network address in this example, we're going to copy the network portion, and then in the host portion, we're going to put all zeros. And that's how we got 155.8.0.0. The broadcast address is just the opposite, so we copy the network portion, and then in the host portion, we put ones, and we get 155.8.255.255. At the end, we have a range of useful or usable IP addresses. This means that all of these addresses can be allocated to endpoints, to computers, to any device that's within this network. So the only 2 IP addresses that we actually cannot use in a range are these 2, the network address and the broadcast address. All right, now let's look at what happens when we change the mask. So here we had /16, and now we're going to use /21. Now we can't really separate the network portion and the host portion that easily. So these 2 octets are going to be the network portion, but then we're going to have some bits in the 3rd octet that are also going to represent the network portion. And then the other half, or in this case, not the half, but the other, so we're going to have 11 bits in the host portion, so the other 11 bits are going to be the host portion. So for this example, we're going to need to write these numbers or this IP address in the binary format. Now it's a bit easier to distinguish the network portion from the host portion. So we're going to look at the first 21 bits. So this is 8 bits, plus 8 bits, that's 16. And then we got 5 bits until here, and that's 21 bits. So the first 21 bits are going to be the network portion, and the rest is going to be the host portion. Now that we've got that figured out, how do we determine the network address and the broadcast address? So to determine the network address, we need to copy the network portion. So we're going to copy all 21 bits from the beginning of the IP address. Those are the bold numbers. And in the host portion, we're going to switch all the bits from the IP address to zeros. So this is the network portion. We're going to copy the first octet, which is 155, that hasn't changed. And then we're going to copy the second octet, which is 8, and that hasn't changed either. But the third octet has changed. So in the third octet, we had 101 at the end. And this 1 has a value of 1. This next bit has a value of 2, but that's switched off, so we don't count that. And then the next bit to the left is 4, and that's turned on, so we do count that, and that's 5 in total. So we need to calculate 101 minus 5, and that's going to be 96. Or you can add these two values, these two ones, which are 64 and 32. Either way, you get 96. And then in the fourth octet, we're going to have all zeros, and that's easy. That's just 0 in the decimal format as well. Now let's look at the broadcast address. So for the broadcast address, we're going to copy the network portion, and that's going to be 155 and 8 for the first two octets. That doesn't change. But then the third octet changes because we're going to put ones in the entire host portion. And that's going to be 103 when we add all of these up. And the fourth octet is going to be 255 because we have 8 ones in the binary format, which is 255 in the decimal format. Now to determine the range, we're just going to go from the next address from the network address and all the way up to the one address that comes before the broadcast address. So the range is going to be from 155.8.96.1 to 155.8.103.254. All right, hopefully that clears up CIDR. We're going to do more examples later, but now we need to cover one more thing. So it's super easy to write a mask like this, but actually when you configure a router or a switch or some servers, you can't really use this format while configuring. So a mask can actually be written the same way as an IP address. 21 equals to 21 ones and 11 zeros. And the way you would write that or type that in when configuring a router would actually be like this. You would translate the binary numbers into decimal values, and that would look like this. So we have 8 ones, which is 255, and then another batch of ones, which is also 255. And then we have 5 ones, and when you add all of those values, that's going to be 248. And then you have 8 zeros, which is going to be 0. So this is what configuring an IP address with /21 mask would look like on, for example, a Cisco router. All right, that would be it regarding CIDR. As I said, we're going to practice some more, so don't worry, just continue to next lessons and hopefully things will start clearing up. Before we go on to talk about subnetting, we need to discuss reserved IP addresses because not all IP addresses are equal and not all of them can be used freely. Some of them are reserved for specific use. For example, all zeros are used as a default route. All ones in binary format and in decimal format, it looks like this. They are used as a default broadcast. So in our previous lesson, we determined broadcast a bit differently, but you can always use this form for sending broadcast packets all ones in a binary format and of course in decimal format. That's what this looks like. And then we have the loopback address range. Most of you are probably already familiar with the address 127.0.0.1, but actually an entire A-class range is reserved for this use. Then we have the APIPA addresses. APIPA stands for Automatic Private IP Addressing, and it's used when your computer is set to ask for DHCP parameters from a DHCP server, but can't really find a DHCP server, or maybe you're not connected to a network, so you can't get to a DHCP server, or it doesn't exist, etc., etc. So when your computer can't get an IP address any other way, it's going to assign an APIPA IP address to itself. Other than that, we also have 3 private network ranges. These are defined in the RFC 1918. RFC stands for Request for Comments, and these are the documents where you'll find pretty much all of known network and other computer-related standards. So the 3 ranges are 10.0.0.0/8. Of course, we've learned in the previous lessons what this means. So pretty much all of the addresses that start with 10 or which have 10 in their first octet are part of one of these 3 private network ranges defined in this RFC. The next one is 172.16.0.0/12. And now it's not that easy to differentiate between octets when we talk about this mask. So I'm going to show it here in binary format. This is not really correct because this would be /16 the way it's shown here. But it's correctly shown in this binary representation. So the first 12 bits of this IP address represent the network portion. So this range actually ranges from 172.16.0.0 to 172.31.255.255. So you can calculate that based on what we've learned so far and check if I'm right. But that's it. That's the second private network range. And the third one you've also probably heard of. It's 192.168.0.0/16. So all of the IP addresses that have 192 in its first octet and 168 in its second octet, and whatever they have in the other 2 octets, they belong to a private network. Okay, now let's talk about the difference between public and private networks, or public and private IP ranges. So these 3 ranges that you see on the screen right now, these are only meant for private networks. This means that these addresses cannot go out into the internet. So they're not routable on the internet. They shouldn't end up in the internet. So there should be no packets in the internet with any of these addresses in the source IP address field or destination IP address field. So these don't exist on the internet. How is this achieved? Well, by using NAT. NAT is network address translation, and it helps us translate our private IP addresses into public IP addresses that are actually allowed on the internet. So the private IP addresses we talked about in the past couple of minutes, they're not even allowed on the internet. So we have to use the public IP addresses. So we have to translate our private IP addresses. The reason why we need to do this is because there are not enough public IP addresses out there for all of us to have one IP address, one public IP address per device or per person. So we have to use private IP addresses in order to save public IP addresses. And then we use public IP addresses. For example, these three computers are going to use one public IP address to go out to this HTTP server or web server in this example. So this server is going to see all three of these computers coming from a single public IP address. So this is how that's achieved. We have a private interface on the router. This is the LAN interface, and its IP address is 192.168.1.1. And we've talked about this in the previous slides. The network part or the network portion of the IP address has to be the same in the entire network. So this is our private facing or private network facing interface on our router. And this is the public network facing interface, or the WAN interface, wide area network interface. And we're going to give it this address, 76.0.13.6. So this is definitely a public IP address. It doesn't belong to any of the three ranges we've talked about on the last slide, and it's not a reserved IP address, so we can use it freely as a public IP address. Now this computer, 192.168.1.5, is going to send a packet. And this packet has a source IP address 192.168.1.5. That's the IP address of this computer. And the destination IP address is going to be 85.202.9.3. That's the IP address of the web server. So when this packet reaches the switch, the IP parameters remain the same. And then when this packet reaches the LAN interface on the router, the IP parameters are still the same. They only change when this packet reaches the WAN, or the outside facing interface of the router. So the source IP address changes from the private IP address to the public IP address. And then this packet is routed through the internet, and finally, when it reaches the HTTP server only sees the public IP address, and it's going to be the same public IP address whether the packet is sent by the top computer or the middle computer or the bottom computer in this example. Now, when the server sends its response, its source IP address, or the source IP address of the response or of the packet, is going to be the IP address of the web server. So it's going to be 85.202.9.3, and the destination IP address is still going to be the public IP address of the router. So once that response reaches the public interface on the router, the IP parameters are still the same. It's only when the packet actually goes through the router is when it's NATed back into the private IP address. So, whoops, I went back. So this is what happens next. Do you see that? So the source IP address remains the same, but the destination IP address is changed from the public IP address to the private IP address. And then the router sends the packet back to the original sender, which is 192.168.1.5 computer. Okay, now that we've covered the basics, let's talk about why do we even need subnetting? Let's look at an example. So here we have a network with a router and 3 switches that are all connected to each other, and then they're connected to a single interface on a router. For this example, we're going to use a class A network 10.0.0.0/8, which means that only the first octet represents the network portion and all the 3 other octets represent the host portion. That means that we can have 2 to the power of 24 different IP addresses. Now, I'm not going to populate all of the computers with IP addresses, but let's say they have something like this. And we're going to talk about an example when one of the computers sends a broadcast packet. So here we have a computer with an IP address of 10.0.0.70, and this PC is going to send a broadcast. So what happens next is this packet goes to the switch. Now, a general rule is that once a switch receives a broadcast packet, it will forward this packet to all of its ports except the port where it received the packet. So what we will see here is that this switch in the middle is going to get a packet, and then all of the other laptops in this switch's network are also going to receive this broadcast packet. Now, the middle switch is also going to forward the packet to all of its ports except back to the port where it received the packet. So this packet is next going to go to the router, the switch to the right, and all of the laptops in the middle switch's network. Now, the router is not going to forward the packet because routers generally do not forward broadcasts, but this switch is going to forward the packet to all of these PCs, to all of the PCs in its network, I should say. So in the end, these are all of the devices on this network that have received this broadcast. Now you may notice that it says security here, and this is a security concern. Generally, broadcast is an enemy of security because the way a network functions normally is that when a computer receives a packet that isn't meant for that computer, is going to drop it. But then if you install, for example, Wireshark or any other sniffing program on a computer, it is going to read all of the packets that it receives, even if that computer wasn't meant to be a destination of that packet. But enough of talking about problems, let's talk about solutions now. I'm going to suggest 2 solutions to this issue, and the issue is a too big network. So we want to segment this network into smaller parts. One way we can do that is using VLANs. VLAN stands for Virtual Local Area Network, and it's used to virtually separate different logical segments of a network. In this example, I used 3 VLANs, 10.0.1.0, 10.0.2.0, and 10.0.3.0. And these 3 networks are appropriately named VLAN 1, 2, and 3. You will notice that all of them are /24, which means that they all belong in different subnets. So this is one subnet, and then this is another subnet. And we know that by looking at their network portions. If 2 IP addresses have different network portions, that means that they are different subnets. So when you look at colors behind laptops, in the first network, we have 6 laptops in VLAN 1. In the second network, we have 2 laptops in VLAN 1. And then in the third network, we have 5 laptops in VLAN 1. So if one of these laptops, let's say this one, sends a broadcast packet, all of the green laptops or all of the laptops that belong to VLAN 1 are the only laptops that are going to receive that broadcast. So even if all of these other laptops are in the same network or are connected to the same switch, they're not going to get that broadcast because they belong to different networks, at least virtually. So that's what you get when using VLANs. Now, the second solution is going to be to physically separate these networks. So we're going to delete the links we have between these switches, and we're going to instead connect each switch to a separate interface on a router. Now, you can't have 2 or more interfaces on a router that belong in the same network. So if you want to have a topology such as this one, you will have to give each interface on a router an IP address that belongs to a different subnet. In this case, the first network or the green network is going to be 10.0.1.0/24. This is the network IP address. And then to the interface of that network, we're going to assign, for example, 10.0.1.1. People or network administrators usually assign either .1, .10, or .254, which is the last usable IP address in an IP range. But for example, let's say that we can give .1 to interfaces. So all of these interfaces can be .1 in the host portion, but then they're going to belong to different networks because their network portions are different. So let's say that the green network interface is going to be 10.0.1.1, and then the yellow network interface is going to be 10.0.2.1, and the blue network interface is going to be 10.0.3.1. Now, the computers or the laptops can have, for example, this one can have 10.0.1.10, and this one can have 10.0.2.10. It doesn't matter that their host parts are the same as long as the network portion is different. So technically, they belong in a different network or they belong to different networks. If that computer or this first computer in the green network sends a broadcast packet, the only devices that are going to receive that packet are going to be the green laptops and the interface, the first interface on our router. There are 2 types of subnetting we're going to learn in this course: fixed length subnet mask subnetting and variable length subnet mask subnetting. First, we'll talk about fixed length. Fixed length means that every subnet in your network will have the same mask. In the example from our previous lessons, whether we use fixed length or variable length subnetting, we will end up having the same mask for each of these 3 networks. Let me explain this example real quick. So we'll look at the first subnet. What's going on with my cursor? Here it is. Okay, so let's look at the first subnet, 10.0.0.0/27. So we have 15 laptops in this subnet. That means we need 15 different IP addresses to be assigned to our laptops. We need one more address to be assigned to our router interface. But we need 2 additional IP addresses for the network ID or the network IP address, and the second one for our broadcast IP address. That means in total, we need 18 different IP addresses per subnet. So each of these networks, each of these subnets needs at least 18 different IP addresses. If we use /27, that means we'll get 32 IP addresses per subnet. How did I get that number? Well, /27 means that the first 27 bits represent the network portion of the IP address, and then the remaining bits, which is 5, represent the host portion of the IP address. So 2 to the power of 5 is 32, which means that we can have 32 different combinations to be used as the host part of the IP address. Let's go to our next example. So here we have 3 smaller networks and 1 larger network. Of course, in all of these examples, the cloud that represents the internet is just going to be ignored. It's just there, and it could be any network. Let's start by counting the number of IP addresses we need per subnet. So we'll start from the largest network on the left. We need 8 IP addresses for 8 laptops, plus 1 IP address for the router interface, plus 2 IP addresses for the network ID and broadcast. In total, that's 11 IP addresses for the largest network. For the other 3 networks, we need 2 IP addresses for the 2 laptops, plus 1 IP address for the router interface, plus 2 IP addresses for network ID and broadcast. In total, that's 5 IP addresses for all of these networks. So this is our request. Create 4 subnets where 3 subnets should have 5 IP addresses each and 1 subnet that needs 11 IP addresses. And here I'm going to give you the solution right away, and then I'll walk you through that solution. The first thing you should notice is that each of these 4 networks that are different have the same mask. Okay, so how did we get here? First, I'm going to mark all the subnets and then populate the number of hosts. We're going to begin from the largest network, which needs 11 IP addresses, and then we're going to talk about the other 3 networks that need 5 IP addresses each. The next thing to be determined is the mask. So in fixed length subnetting, all of the subnets are going to have the same mask, and the masks for all of the subnets is determined by the largest network. So we just need to make sure that the largest network has enough different IP addresses to cover all of its hosts. For 11 addresses, we're going to need 4 bits. 2 to the power of 4 is 16. If we used 3 bits, that wouldn't be enough. 2 to the power of 3 is 8. So that's not enough for our largest subnet. If we were to use 5 bits, that's too much. That's wasting IP addresses, because that's 2 to the power of 5, that's 32. That's 32 different IP addresses. We need 11, and we can get 11 by using 4 bits. So that's what we're going to do. Mask /28 is perfect for us because that means we'll use 28 bits for the network portion and the remaining 4 bits for the host portion. Again, 4 bits is enough because 2 to the power of 4 is 16. Now we'll just copy that into all the other subnets. Since this is fixed length, all of the subnets have the same mask. Our remaining fields are going to be network ID, which is the network IP address. And then the other, or the last column, is going to be range of useful addresses. So the network ID we're going to begin with is 192.168.1.0. Range of useful IP addresses will begin at 192.168.1.1, And the last useful address is going to be 192.168.114. 192.168.115 is going to be our broadcast address that we can't allocate to a host or a router interface. So the next network ID, the network ID for our second subnet is going to be 192.168.116. And don't worry if you're not sure how I got here. I'm going to explain this when we go through our more complex examples later. But for now, since these are very small subnets, you can see it for yourself by using simple math. So 2 to the power of 4 is 16, as we've said at the beginning. And here we have actually used exactly 15 IP addresses, or exactly 16 IP addresses counting the 0. So it's the 0th IP address, and then the other 15 are going to be 14 useful IP addresses, and the 15 is going to be broadcast. So the next IP address is 192.168.116, and we're going to use that as the network ID for our second subnet. Range of useful IP addresses in the second subnet is going to be the next 16 IP addresses as in the previous example, from 192.168.117 to 30. And then 31 will be the broadcast IP address for the second subnet. And then the network ID for the third subnet is going to be 192.168.132. And then again, we're going to use the next 16 IP addresses in that subnet, where 192.168.147 is going to be broadcast, and then 192.168.148 is going to be the network ID of the fourth subnet. And then the range of useful IP addresses for that subnet will be from 192.168.149 to 192.168.162. And the broadcast IP address there is going to be 192.168.163. And if in this example we had a fifth subnet, then the network ID for that subnet would be 192.168.150. So as you can assume, this is very, very basic. In the following lessons, we'll go through more complex examples. So just keep going and you'll be a pro very, very soon. Time to talk about VLSM. VLSM stands for Variable Length Subnet Mask, and the goal of this type of subnetting is to save as many IP addresses as possible. Let's look at the definition. So, unlike fixed-length subnetting, variable-length subnetting creates a hierarchical IP address space, making it possible to create subnets without wasting a large number of addresses. We're going to use the same example we used in the previous lesson, only this time we're going to adapt the mask when we get to the smaller networks. So we're not going to use the same mask for all 4 networks. So the request was to create 4 subnets where 3 subnets should have 5 IP addresses each, and 1 subnet needs 11 addresses. Let's remind ourselves what was the solution when we used the FLSM technique. We had 4/28 subnets, which means each subnet has 2 to the power of 4, which is 16 different IP addresses. And only in the first subnet, we actually needed that many IP addresses. In the other 3 subnets, we only needed 5 IP addresses. So let's look at the VLSM solution. Now for the first network, it's still going to be /28 because, as I said a minute ago, we need 11 addresses in the first subnet. So we're going to use /28 because that gives us 16 different IP addresses. The network ID also remains the same, so it's going to be 192.168.1.0, and the range is also going to go from 1 to 14. Dot 15 is going to be the broadcast IP address. Now let's determine what's going to be the mask for the second subnet. The second subnet, just like the other two, need only 5 IP addresses. So we can give it /29 because that gives us 3 bits for the host portion, which means we can create 2 to the power of 3, which is 8, different IP addresses for hosts. The network ID is again going to be the next free IP address after the broadcast IP address in the previous subnet. So the broadcast address was 192.168.1.15. So the network ID for the second subnet is going to be 192.168.1.16. The range will be from 117 to 122 because this time we're only going to use 8 IP addresses. So for the other 2 subnets, it's actually going to be easy because the mask is the same. We only need to calculate the range. So for subnets 3, mask is /29. The network ID is going to be the next free IP address after the broadcast address of 192.168.1.23 from the previous subnet. And the range is going to go from 25 to 30, and then 31 is going to be broadcast for subnet B. So the network ID for the fourth subnet will be 192.168.1.32, and the range is going to go from 33 to 38. Let's compare our VLSM result with the FLSM result. So this is FLSM and this is VLSM. When you look at the last IP address we used in the fourth subnet for FLSM, it was 192.168.1.62. And then the fourth subnet, or the last IP address in the fourth subnet, when we used VLSM, was 192.168.1.38. So this shows you how many IP addresses we actually saved only by using the VLSM technique. One last topic we need to discuss is summarization. I'm going to explain summarization through an example, and we'll use a network we used in our previous lessons. All right, let's say that our router, the only one that we have in our network, instead of being connected to the internet, it's connected to another router, and then that router is connected to the internet. We're going to assume the IP addresses that we decided to give these networks in our previous lesson. So the network between the router and the switch on the left is 192.168.1.0/28. And then the 3 switches that have only 2 laptops connected to each one of them are /29 networks. And then we have another network between the 2 routers, between our old router and our new router. That's going to be 192.168.1.40. And notice that if we have a /29 here in this network, 192.168.1.32/29, that means that our last usable IP address in this subnet is going to be 39, and that's going to be the broadcast. So the next network ID, or the next network IP address, is going to be 192.168.1.40. And we're going to give it /30 because this is a point-to-point network. And a point-to-point network between 2 routers only needs 2 usable IP addresses, one for the interface on the first router and the other one on the interface on the second router, and then we need the network ID and the broadcast IP address. And with /30 network, that's what we get. We get exactly 4 IP addresses. The only network left to define is our public network, which is the network between our new router and the internet. So we're going to use 777.0/30. Now let's separate our private network from the public network. So this area right here is our private network. Now, if we were to look at this network from the internet, and just for the sake of this exercise, let's forget about these IP addresses actually not being routable on the internet. So if we had a router someplace on the internet, it would have to know about all of these subnets. So it would have to remember a route for 192.168.1.0/28, 192.168.1.16/29, 124/29, 140/30, etc., etc. In order to avoid that, we could just say to that imaginary router, all of the addresses or all of the networks that begin with 192.168.1 are here. So they are on this side of this public router, so to the left. So the only thing you need to do is just send a packet to this router, and then this router is going to know where all of the specific subnets are. The problem with that is if we had, for example, 192.168.1.128/30, for example, network somewhere else on the internet. So that would be an issue because we would have said to that imaginary router, okay, all of those networks are here. But then if one of those networks such as 128 or 192 or something like that appeared someplace else, then our routing would be incorrect. Because of that, we're going to scratch our /24 mask, and we're going to create a more specific mask to only cover those IP addresses that are in our private network connected to this router. What we're going to do is we're going to look at all of the networks that we have in this network, or all of the subnets that we have in this network. So it's 192.168. All of the subnets have their first octets like this, 192.168. And then they also have 1 in their third octet. But then the fourth octet is different in every subnet. We're just going to look at the network that has a highest value in its fourth octet, and that's this network, 192.168.1.40. So we need to think about what's the last usable IP address in this subnet, and that's 43. So 40 is the network ID, 41 and 42 are the two usable IP addresses, and then 43 is broadcast. Okay, so here we have all zeros, and this is our definite network portion if the mask is /24, but then this value is 43 in decimal format. And in order to create a summary subnet or a summary IP address, we need to look at all of the bits that are the same in all of our subnets. So it's definitely going to be 192.168.1. We can already see that without doing any math. But then the first two bits in our fourth octet are going to always be 0. That means that the number of bits that are always the same in all of our subnets is going to be 24. So this is 24 plus the 2 bits from the fourth octet. So that's 26. And that's going to be our new subnet mask. So 192.168.1.0/26 is our summary address for this entire network. Now we are safe in case a new network appears. For example, let's say that's network X and its subnet is 192.168.164/26. So now we're okay because all of our IP addresses in our existing network or our existing summarized network are going to range from 192.168.1.1 to 192.168.163, which is actually what you would get if you would try and make a broadcast IP address for this subnet. So if this were one simple subnet and you knew nothing about it, just looking at it from the outside, and you try to get its broadcast address, that's the last IP address in this subnet, it's going to be 163. So the very next IP address, which is 164, is a perfectly usable IP address that can be used in any other subnet. So the range for this new network X would actually be 192.168.165 to 127. So we're perfectly safe to use this summarized IP address. But don't worry, we're going to practice some more, and we're going to go through some more examples in our future lessons. Let's dive into our examples.